Oh, hello. I didn't see you there. Today we're going to talk about the Feynman Sprinkler. So named because while he was a student at Princeton, Richard Feynman wondered what would happen if you had flow into a sprinkler instead of out of it.
So he designed an experiment. He placed an S-shaped sprinkler underwater attached to a vacuum, and rather than blowing water out, it would suck water in.
Feynman left the results of his experiment ambiguous. Today, as introductory fluid mechanics students, we investigate this problem.
So this is our sprinkler. We attach a shop vac to the bottom and it blows or sucks air out through this part of the sprinkler, which then induces a moment and you get rotation. We're going to approach this analysis by thinking about, with flow moving in or out of this pipe, how much torque is going to be required to hold this still. So we're going to set up a control volume on this arm of our sprinkler to analyze the moments about this point. We have one inlet and one exit, or in the case of the reverse sprinkler, we have one inlet and one outlet. So to set up our system on paper, next step is we're going to set up our control volume and control surface. And then we're going to use the Reynolds transport theorem. And then we have to make some assumptions. So we're going to assume that our system is steady state. There's uniform flow at both the inlet and the outlet, that we have incompressible flow, and that our control volume is inertial and undeformable. So the steady state assumption helps us get rid of our storage term, and then we're just left with the flow in and the flow out across our control surface. So we have flow going out, flow going in. The flow in does not induce a moment about point A because the force associated with that flow is directly through the point at which we're taking the moment about. So the only force we're left with is the one induced by V2 right here on the edge. And because we're in equilibrium, we're assuming that this is still, so it's in equilibrium. So we're going to have some counterbalancing moment. Call this M. It's going to equal M plus since our moment arm and our velocity are perpendicular to each other, the cross product goes away and we just have the magnitudes multiplied by each other. Density times velocity. And then the dot product, since they're perpendicular, and this one they're facing the same direction, so the dot product is positive. And this is our expression. So this is going to equal minus M plus M dot R. And there you have it. So this is our moment that we have to apply in order to keep this thing still. Dot RV. So that's for the regular sprinkler. But what about the reverse case? I'm going to pass you off to Jordan to finish that analysis.
Thanks, Charlie. One would think in the case of the Feynman Sprinkler that the calculations would be the same, just with opposite velocity. However, it's not that simple. Let's take a look. This is the system of the case that Charlie just analyzed. In this case, the pressure at the outflow is equal to ambient pressure, and there are no external forces on the system due to pressure. And so for this system, we made these assumptions. However, in the second case of the Feynman Sprinkler, we can no longer make these assumptions. The streamlines are bent at the entrance to the pipe, so we no longer have uniform flow. Well, we will now have to account for that loss due to viscosity. Also, the pressure at the inlet is no longer equal to ambient pressure as in the first case, so we have to account for this new inlet pressure in our analysis. We could use the Bernoulli equation to find this new inlet pressure, but that isn't a very good application of the Bernoulli because the new flow profile at the inlet isn't uniform and we have viscous losses. So we will use the conservation of energy equation with the head loss term. Due to large reservoir assumption, we can neglect the initial velocity. Since P2 is gauge pressure, we can set P1, which is atmospheric pressure, equal to 0. Also, there's no elevation change, so we can set Z2 equal to Z1 and get rid of that term. The equation for head loss is right here. KL is the loss coefficient, a function of the geometry of the system. According to Colorado State Engineering, we can assume KL is equal to 1 for our system. The right hand of our equation is now equal to 0. Knowing that KL is equal to 1, the pressure is now equal to rho and velocity. Knowing that velocity is a function of flow and area, our pressure is equal to rho Q V over A. Let's use this new pressure to find the torque required to keep our sprinkler still. Your move, Scott.
Whoa! I'm feeling the pressure. Let's see what the math says. The first thing I'm going to do is solve for the torque caused by the pressure that Jordan had derived. We rearrange the equation to find the area of the nozzle. Solving for the torque caused by the pressure, we substitute in our area. Note that flow is a negative dot product. We solve and reduce to mass flow rate times R times V. Now, solving Reynolds' expression for flow going into the sprinkler, we have a negative moment. We solve again and get m dot RV. Finally, we use our moment equilibrium equation, TA being the moment around point A, TP being the torque caused by the pressure, and Reynolds' expression for the total moment. Solving for TA, we plug in MA, and we plug in our torque caused by the pressure. And our torque is 0. So what does this mean? This means that no external torque is required to prevent the Feynman sprinkler from moving. But that's enough math for now. Let's go put this theory to the test.
So in this case, we have outflow. This is the normal case. All right, this is the Feynman sprinkler. So we're gonna have air being sucked into our sprinkler, and let's see what happens. So from our equations, we calculated that there would be no net torque on our sprinkler system. But we didn't account for potential frictional losses inside the pipe that might result in a different effective pressure than the one we calculated. So there might actually be a net force on the pipe. And we can see that in videos online where people have movement in their Feynman sprinklers.
But I didn't see our Feynman sprinkler move, Charlie. Do you think it has to do with the friction due to the T-pipe?
Maybe, Scott. What do you think, Jordan?
So we use this T-pipe so our sprinkler could actually rotate. However, when we turn on the vacuum, the pipe gets sucked down onto this T-pipe. Now, the force from the pressure over here has to overcome this friction, and it just does not happen in our sprinkler.
So that makes sense. That's why it didn't move.
Yeah.
And that's it for our Feynman sprinkler experiment. I'm Scott.
I'm Charlie.
And I'm Jordan, and we'll see you next time.
All right, let's do this.
3, 2, 1.
Oh, we're a little late.
Whoa, I'm feeling. Whoa, I'm feeling. Whoa, I'm feeling. Whoa.
No.
Whoa,
I'll-
Whoa, I'm feeling the pressure.
No.
Our Feynman sprinkler experiment. I'm Scott. Experiment. I'm Scott.
I'm Charlie.
And I'm Jordan, and
Just stop.
I'm Scott.
I'm Charlie.
and I'm Jordan. See?
That's it for our Feynman sprinkler experiment. I'm Scott.
I'm Charlie.
Charlie! No!
I didn't laugh.
Yeah, you giggled.
I'm Scott.
I'm Charlie.
And I'm Jordan.
We'll see you next time.
Okay.